Hey everybody, it's Dr. J, and today we're talking about valence shell electron pair repulsion theory. Let's talk chemistry. Alright, so let's talk about VSPER theory. I'm not about to say that long word all the time. It's VSPER theory, everybody. Alright, so VSPER theory, this is just a simple model that's going to basically help us determine a molecule's shape. Okay, so a couple different things before we dive in as far as how we're going to use this. Basically, we need to understand this little graph over here, right? We got our central atom and we have our other atoms that we're going to be bound to, right? Now, we understand that those electrons, those valence electrons, are the things that are bonding, right, between the two, right? And we call those electron groups, right? These are the electron groups, these electrons. These atoms, right, they like to be as far as apart as they can be. And when they are as far as apart as they can be, they're stable, okay? This is going to give off certain geometries every single time, right? Now, these geometries we're going to talk about in literally 30 seconds, all right? But I just want everybody to understand, because of these electron groups, right, these electrons, they like to be far apart. And because they're far apart, depending on how many electron groups you have, that's going to determine your geometry, right? So we're actually able to determine our geometry based on, right, our electron groups. So couple of steps that you're always going to have to do with VSEPR theory. The very first thing is that you're going to have to draw your Lewis structure. So you do not know how to draw Lewis structures, check the previous video in this playlist here. Once you have your Lewis structure, you then will count your atoms in lone pairs and then arrange them as far apart as you can. And once you have those in place, then you can determine your name of your geometry based on the atoms that you guys have. Okay, so we have our geometries here: linear, planar, trigonal, tetrahedral, trigonal, bipyramidal, octahedral. We're going to talk about all these right now. Couple different types of geometries. Let's start with the very first one, linear geometry. Right? So these are the molecular shapes we're going to talk about. The first one is linear. So linear is basically when there's going to be two electron groups around your central atom. Okay, and because there's two, right, the bond angle, because we understand that they like to be far apart, it's always going to be 180 when you have a linear geometry. So when we look at this example, right, a linear geometry that we have, right, beryllium and chlorines, two of them in this case, we're going to have two of those groups on either side. And because they're on either side, we're always going to have this bond angle of 180. Always will be the case, right? This is as far as they can be, and they like that. And because they like this, this is our linear geometry. Okay, now a couple different things. How we're going to think about this. What if we have two double bonds, right? Same thing is going to apply. Carbon dioxide, even though it's two double bonds, this is still a linear geometry, right? The oxygens, as far as they can be in this case, right? So if it's a double bond, triple bond, single bond, it does not matter, right? Think of these as being arms, right? Depending on how many arms you have, that's going to determine, right, your bond angle. So for linear geometry, I got two arms. Okay, so linear geometry, two arms. Trigonal planar geometry. This is when we got three electron groups or three arms. Now, do I got three arms right now? No, I don't. Okay, but this is what happens when you have three electron groups around your central atoms. Okay, so because we're always going to have these three electron groups, essentially we're always going to get the same type of bonding angle. In this case, we're always going to get a 120 bond angle. So an example of this is BF3, right? BF3, I got a fluorine, fluorine, fluorine. What we're going to see is I'm going to have a 120 angle right here, 120 angle right here, and a 120 angle right here. Because of this 120 angle, I'm always going to have a trigonal planar geometry. Always is going to be the case if I got three electron groups. Now, one thing I will like to notice, this is kind of an estimate with the 120. If we think about for formaldehyde, right, this central is our carbon, and then we got our three electron groups or three arms, oxygen, hydrogen, hydrogen here, right? So it's going to have a trigonal planar geometry, of course. But depending on your electron groups, right, you might have a slight difference in a bond angle. So in reality, this is actually the angles for them, right? 121.9, 121.9, and then the hydrogens in this case are a little bit closer at 116. Now, like I said, very close to 120. All right, so for the most part, this is very close. It works, but just, it's possible to have a slightly difference in the angles. But once again, these are predicted values. All right, but we can see with the predicted values, it's still, spot on at 120. So next we have tetrahedral geometry. So this is when we have 4 electron groups or 4 arms, okay, around our central atom. And whenever we have 4 around our central atom, right, we're going to have a bond angle of 109.5. Okay, so each one of these are always going to be 109.5. Okay. If we move on to the next one, we have trigonal bipyramidal geometry. So this is when we got 5 electron groups around the central atom. So this one's a little bit different as far as compared to the rest ones. We actually are going to see 2 angles here. So with trigonal bipyramidal, basically these 2 angles, we're going to see that we're going to have 3 groups in one plane and then 2 in our axes. So if we look here, PCl5, here's the Lewis structure, right? But when it comes to how they're actually arranged, how these compounds are actually going to be arranged with the atoms, the chlorines, 3 of the chlorines are going to be in the same single plane. All right, in this case, they're in the equatorial position, right, in this single plane, and it's a 120 distance between these 3 chlorines here. Now, my top and bottom chlorines are in my axial position. Okay, so basically there's a 90-degree angle between my top and here. Okay, and then same distance right here, 90 between those 2 here. Okay, so in this case, trigonal bipyramidal, we see 2 different bond angles. And then we have octahedral geometry, right? So this is when we have 6 electron groups around our central atom. Okay, so because they're octahedral, basically they're all going to have a 90-degree atom. Okay, 90-degree angle. All right, but in this case, we got 6 of them. All right, so when we look at SF6, right, I got 4 around my plane, and then I have 2 in my axial position. All right, so this is always the case for octahedral geometry. And guys, this is like, the step 4, right? This is why you need to know how to do Lewis structures, right? If you got the wrong Lewis structure, you will get the wrong shape, right? Because we're basing the shape off our Lewis structures. So please, if you don't know how to do Lewis structures, please check out the previous videos.